Hello, guys. So today we start a new and wonderful topic. So this is lecture 5, maybe, yeah. And we will talk about complex numbers. So this is a large topic, and we will discuss various aspects of that. And I don't know how familiar are you with complex numbers, but I will definitely formulate and prove all the basics, but also pretty fast we'll go to more advanced ideas related to them. So maybe even if you will be bored at first, later on we will come to more interesting things. So complex numbers. Let me kind of draw this beautiful notation for them. And probably all of you know that complex numbers are these weird numbers a plus bi, where this a and b are just real numbers, and I has a property that I squared is -1. And maybe at first when you see this object, you find it a bit peculiar, and of course you would immediately start asking questions whether complex numbers exist or not, and so on, because how can you take a square root of -1? Surprisingly, the question of their existence, which at first was such a mysterious topic, and of course there were a lot of debates about it, the question of their existence is extremely simple. So using modern language with modern approach, I will prove that complex numbers exist and will construct them in a few minutes, and this will take me, I don't know, like 3 minutes or something. Much easier than polynomials and along the same route. So now, from modern perspective, there is no question of whether they exist or not, but rather maybe what is interesting about them and why would you care. And why an object in mathematics is interesting, this is of course a question which usually has a lot of answers, but in many cases it starts with some appearance of this object, which might be very much not the most important, very much not the most natural, but just some, where you can notice that maybe taking square roots of -1 might help. Historically, the story started to develop, the complex numbers started to develop with Italian attempts to solve cubic equations like x cubed plus px plus q equal to 0. And the reason why they appear there is, of course, though people were trying to solve equations which had roots, like finding real root of something like that. So nonetheless, if you want to write down a formula, which will be a relatively simple formula with radicals, with cubic roots and square roots, finding a root of this polynomial, you will almost unavoidably have to work with complex numbers while you are trying to solve it. And so at first they appeared more as a computational trick maybe, but slowly they start to appear in work of Euler and in work of Gauss and number theory and so on. And already by the end of 19th century in mathematics they were everywhere. So in all areas of math it was clear that this is a fundamental object. And a little bit later, in early 20th century, they came to physics. At first, they came again as some kind of a computational tool in computing with electric networks, things like that. But before quantum mechanics, they were pretty much a mathematical abstraction. And then in quantum mechanics, everything is built on complex numbers. You might have heard of the fact that wave functions are added and they are complex valued functions. And if you want to actually compute real probabilities of different events, in the process you will have to work with complex numbers, and sort of the feeling is that they are describing reality on a more fundamental level. So now complex numbers are everywhere accepted as something very, very real, if you excuse me for this pun. So, okay, but let me kind of give you a way to come across the idea that they might exist and might be useful from the perspective of our course. So there are 2 roads I can take. Let me first mention route number 1, and then I will just very quickly move to another one. So if you already know what is sine of x, which you might from geometry, high school, and so on. If you already know what is cosine x, which you again might know from the same reasons, these are very geometric things related to triangles, very old in some sense. And then you might also know what is exponent. And again, all of these three functions are just a real variable, are very well understood and have nothing about complex numbers inside. And then you might start to, if you study their expansions in power series, which we encountered as formal power series, then you very well know what you will get. So you will get this beautiful, a bit unexpected expressions at first. And then you notice that there is something about these expressions which relates all three of those. And the relation is a little bit peculiar. So let me first finish writing. So at first you might think that they are related very closely, because basically for every term in the formula underneath, you will see for a term in the formula for cosine or sine, which will kind of match it. And it has the same denominator, same power of x. And the only problem is sine. So it's not quite true that e power x equals to sine of x plus cosine of x. That's just not true. And the reason is that we have weird signs. But then you might notice that if you just imagine that there is this thing of taking square root of -1, then if you plug in instead of x just ix, whatever that means, and just formally write it down here, taking the square of I being -1 and so on, and then you will come to plus ix minus x squared over 2 factorial minus x cubed over 3 factorial and so on, and then suddenly you get that your expression has cosine x as a first like even degree part plus I sine x as odd degree part. And not only you come up with this beautiful formula, which is called usually Euler's formula. If you plug in pi, you will get this famous e power I pi equals to -1 statement. Not only you come to that, but more importantly, you kind of start to understand that sine, cosine, and exponent are weirdly related. If there is any relation, it should go through these complex numbers, which indeed is the case. So currently, we definitely think that exponent, cosine, and sine are more or less all the same things, parts of the same object, which is what's called complex exponent. And we will talk about it a bit later. But if this is, so this is the idea where you need to mix your knowledge of these real functions and power series expansion. Power series expansion is not high school, so you might just learn it recently or maybe just in this course. This is something you might already feel is weird. So let's just stick with this cosine and sine story. How to come up with its relation with exponent. So here is the idea, and complex numbers. So one of the first things you learn about trigonometric functions are these weird rules that they satisfy lots of trigonometric identities. Among most famous are sine x plus y equals sine of x cosine of y plus cosine x sine of y, and cosine x plus y equals cosine x cosine y minus sine x sine y. So in modern mathematics, a lot of people despise actual explicit identities. I don't share this opinion. I think explicit formulas are very beautiful, and sometimes they have more meaning than you expect they would. And this is definitely the case here. So if you want to get deeper into their nature, like why the strange rules are actually true, one way to do it is to iterate them. And I'm not going to take sine of sum of many variables. Let me just instead look at sine 2x. So sine 2x equals to 2 sine x cosine x, which is again a formula you might know very well. Cosine 2x equals 1 minus 2 cosine squared x. I hope. Nope. Okay, and then you can come up with sine 3x. And let's see, so this is sine 2x plus x, which is sine 2x cosine x plus cosine 2x sine x, which is 2 sine x cosine squared x. I will just do sine and cosine of 3x, and this will prove my point, hopefully. Plus 2 cosine squared x sine x minus sine x. Is it right? Mm. 2 sine x cosine squared x. Sorry. Let me instead here use another formula, which is equally true, which is cosine squared x minus sine squared x. And so here I will have instead 2 sine x cosine squared x plus cosine squared x sine x minus sine cube x. Fine. This can be simplified, and so we see that this is 3 sine x cosine squared x minus sine cube x. And if you do similar thing for cosine 3x, you will also get something quite simple. So it's cosine 2x cosine x minus sine 2x sine x, which is cosine cube x minus sine squared x cosine x minus 2 sine squared x cosine x, and again it simplifies cosine cube x minus 3 sine squared cosine x. And let's stop here, but if you are a 19th century mathematician, what you would do, you would compute 10 next cases. And you will get lots of formulas which will become very big, and you will stare at them for a while, and soon enough, maybe already here, you kind of notice that they have something to do with binomial formula. And you see that sort of this is already visible here, because here you have two squares. Let's ignore signs. And here we have this 2 sine x cosine x, and they sort of combine into kind of sum of square of sum formula. And similarly here we have 3 sine x cosine squared x minus sine cube x and cosine cube x minus 3 sine squared x cosine x. And again, they sort of combine to the sum of two cubes for cube of sum formula. And if you continue to do it over and over, you will get more and more such relations. And then you might try to actually write it. So there should be a way to write it in a form a plus b n sort of equals whatever a n plus n choose 1 a n minus 1 b plus and so on. So there should be some relation, and it's clear from looking at these powers that maybe we should put a equal to sine x and b equal to cosine x, and this might be the first idea, or like minus cosine x maybe. But if you do just that, you will see that though it looks kind of very close, all the terms will match. Again, signs will go wrong. Also, you don't expect sine plus cosine power n be the same as sine of n plus cosine of n or something like that. So that can not be right. And then you notice again, or if you are sort of genius enough, you notice again that if you just add, instead of just sine x, you will add everywhere this I, you will get something very beautiful. So if you just accept this little rule of arithmetic with I squared equals to minus 1, whatever that means, then you can just write down sine of x, cosine x plus I sine x power n is equal to cosine nx plus I sine nx formula. So at first you might think about this formula as, a quick way to present or formulas for sine of iterated argument and cosine of iterated argument. And indeed, this is helpful. By the way, there was a problem about pi squared over 6, and there was some formula for like cotangent of something is solving some equations, and this is the way to do it, using this. So at first you might think of it as just a computational trick, like mnemonic, how to remember these formulas. And then you might try to think whether there is anything more to that. So, and here is the things I would do if I would just, okay, so we got this idea for variance integer n. And notice it's true even for n equal to 0. So you might start thinking, what about n equal to -1, for instance? And then you check, so if you have this cosine x plus I sine x inverse, that's 1 over cosine x plus I sine x, and then you just multiply on cosine x minus I sine x. So the statement is that it actually equals to cosine x minus I sine x. This is what predicts binomial formula, if you wish, for minus. Wait a second, what I'm saying. Yeah, so our formula predicts this relation, because if you plug in instead of n minus 1, you will get cosine x minus I sine x, and then you can just see that if you just multiply on cosine x plus I sine x, this is true. So that's very meaningful, and so we kind of expect that this formula is true for all integers. And then you might think, okay, how would you prove that? So of course, one way to prove it will be by induction, involving maybe properties of binomial coefficients and so on. But after a while, you might wildly guess that actually maybe this is true because a more general statement is true. And indeed, you can check that cosine x plus I sine x times cosine y plus I sine y, if you open brackets and uses two properties of sine and cosine of sum, you will get, of course, cosine x plus y plus I sine x plus y, and then you get this formula just doing it n times with the same argument by induction. Now this induction is trivial. And in this kind of way, you can get an idea that, okay, there is something in it. So somehow looking at these combinations, cosine x plus I sine x is meaningful, and they have a beautiful property that when you multiply them, then this x and y add, and this property of algebra of complex numbers actually helps to make sense of trigonometry. And this is actually indeed helpful if you are whatever preparing to some crazy high school exams with a lot of trigonometric formulas. If you just use complex numbers, a lot of them will simplify greatly. Not all of them though, but most. So okay, so I wanted to emphasize the idea that sometimes you can come across existence of complex numbers in some sense, just looking at them as a trick to simplify some computations. But after you understood that you might want to have them at your disposal, you might want to just be able to write things like a plus bi naturally, then you need to come up with some definition. And what distinguishes mathematics is that we always are looking for, precise definition, not just saying, let's take this number a plus bi, and we do this and we do that, and we hope we will never get into trouble. We want to explain why this procedure exists. And as I already mentioned, with modern technology, it's surprisingly simple. So I will do it in the next few minutes. And then we will look at this formula more closely and try to find a geometric interpretation for that, and then move to using complex numbers for some ideas in geometry. Okay, so next bit, construction. So okay, so what we want to mimic? We want to mimic construction of numbers a plus bi, where I squared is -1, and we know how to add them. This is sort of something we definitely want to be able to do, and we add them as just using simple algebraic rules. and we want to be able to multiply them, again, according to sort of distributivity law. AC, then BI times DI is minus BD plus BC plus ADI. So that's as simple as that. Okay, that's not the definition. That's what we want. But definition is very straightforward. So complex numbers are, by definition, just pairs of real numbers. So let's not even worry about what this plus I and so on mean. Let's just call this pair a complex number, Z. Okay, you think that this gives me nothing, but actually it gives a lot, because now I can sort of start to define arithmetic operations in this way. So define two maps. So Z1 plus Z2, where Z1 is A1 plus B1, sorry, A1 B1, and Z2 is A2 B2, as A1 plus A2, comma B1 plus B2. So now we have addition of complex numbers. So this is just the way we add them. And if we want to multiply them, we just use this formula as A1 AC, A1 A2 minus B1 B2, comma, A BC AD, A1 B2 plus B1 A2. So, okay, this is addition, this is multiplication. And now a very important fact comes, so proposition. So C is actually a field. And it just means that we can do all usual things with these operations. So addition is associative, commutative, multiplication is associative, commutative. So then there are such things as zero. So zero is clearly something which when you add, you don't change it. And this is just 0, 0. And multiplication, we need to find what is 1 here, and this should be some pair of numbers which when you multiply, you don't change it, and very quickly you understand that this is 1, 0, and of course this is what you expect if you believe that we are talking about A plus BI after all. And then maybe the most surprising property is miraculously multiplication associativity. So if you will try to do that, you will have to actually open brackets in some pretty complicated expression, and it will work out. So just take 3 numbers and open brackets, and this is a good exercise to do, because at first it might be like, why that happens? So finally, field is supposed to have an inverse, and you can just solve this as an equation. So let's suppose I know A plus BI and I want to find the C plus DI. So then I have kind of equation A comma B times C comma D should equal to 1, 0. And let's suppose I know that C or D is not equal to 0, because otherwise I'm trying to divide by 0. Sorry, and I'm trying to find this AB. So, and then I know that I have basically a system of equations. So AC minus BD equals to 1, and AD plus BC equals to 0. So that's something to solve, and it might take you a few minutes, but eventually you might do it. So can I do it? I mean, maybe one way is to actually just write, so I'm looking for A. So let's write A as minus BC over D, and then I plug in and I get minus BC squared over D minus BD equal to 1. And I get pretty interesting statement that minus B times C squared plus D squared equals to 1. And so B equals to minus 1 over C squared plus D squared. Is it right? Yeah. And then A should be equal to... Wait, something is wrong. Let's see. So I meant d. D over c squared d squared, and then a equals to minus bc over d. So this is the same as just substitute d with c over c squared plus d squared. I get this one. So I got a formula, and notice that beautifully this thing is strictly positive, just because, you know, we have two real numbers, one of them is not zero, so sum of squares is positive, and so such numbers exist and they are unique. So this is basically a draft of a proof that C is a field. So now we can work with complex numbers, and we know that all operations are working as we expect. So the next observation is that, okay, the main miracle is, so first miracle is that they should sort of contain real numbers. So we know that real numbers are basically numbers with b equals to 0, and let's just define a comma 0 as a. So here there is something to prove, and the proof, the statement is that actually there is a bijection between real numbers and pairs real number comma 0, which sort of takes your real numbers into complex numbers, and this is injective math, simply because, I mean, if two numbers coincide, a will coincide as well. And also it sends addition and multiplication exactly to the same operations here, and for this you need to take your formulas and plug in the case when sort of b's are 0, you will see that you just multiply a's, nothing else happens. And so you can actually think of this as real numbers inside your complex numbers. And then, of course, if you have a, b, so now you can nicely write it as a plus 0 comma b. And then a little exercise is that 0 comma b actually equals 0 comma 1 times b comma 0, which is just b times 0 1. And again, you just use this multiplication formula for that. And now you are in the game, because now we can just use using our notation basically, a comma b equals a plus b times the strange number 0 1, and this is something special. There is, I mean, we need to introduce notation for it, and of course we just call it I. And then 0 1 squared, according to our formulas, is nothing but minus 1 comma 0, which is minus 1 according to our convention, and pair a comma b is now identified with a plus bi. So that's really simple. Next question is, okay, so let's just think again. So we were dividing them, right? So this division gave us a formula for 1 over a plus bi, and if you have already seen these tricks of getting rid of something like square root in the denominator, you know that you should sort of multiply on a minus bi, because if you do that, it's really easy to see that this product will be actually real. And so you get a minus bi over a squared plus b squared, and this recovers our formula which we got here in slightly different terms, that the inverse of a plus bi is a over a squared plus b squared minus b over a squared plus b squared I. Okay, so, and by the way, this deserves some notation. So if you have a complex number z being a plus bi, people usually note it by z bar, they conjugate a minus bi. So, by the way, this conjugation has its interesting operation on its own. And I can give you a little hint. So the reason why conjugation is so important will be clear to you after you learn what's called Galois theory, because Galois theory is kind of generalizing this idea of conjugation of complex numbers to wider set of phenomena. But why this operation has a lot of beautiful properties it has, there is a good explanation. So let me actually maybe first formulate the properties, and then I will give the explanation. Okay, so this conjugation again. So we start with z a plus bi, and going to z bar a minus bi. It has lots of beautiful properties. So let me formulate the two which are the most important. So this one is the first. Not surprising, to be honest, just open, I mean, if you a plus bi, c plus di, you will get it. But the second one is much more interesting. So it tells you that conjugating the product is product of conjugation. And in particular, since these two things are true, you can imagine that if you take a conjugate of something very complicated, like 1 plus z100 minus I z cubed plus 3z, something crazy. So you can apply these rules consequently and first write it as a conjugate, sum of conjugates. And then, so let me say plus minus I z cubed conjugate plus 3z conjugate. And then, so for real numbers, conjugation does nothing. For powers, since conjugation of a product is product of conjugations, this will be just z100. For product, again, you need to conjugate left and right, and minus I will go to I. According to that, we have plus I z bar cube plus 3z bar. Something like that. So basically, applying conjugation is very simple. You kind of substitute, to polynomials at least, you kind of substitute everywhere z with z bar, and sometimes switch signs before every I. And so this is an exercise. Please check that if you have never done it. It's a very simple but very important thing to do. But then you might ask, like, why that magic happens? Why conjugation has these beautiful properties? And the answer is because if you think about it, so imagine you are looking at the square root of 2. So you kind of know that square root of 2 is 1.4, I guess. But actually, this is a little misleading, because if you are just seeking a number such that 2 equals to this number x squared, then you can as well take minus 1.4, and this squares to 2 as well, just because minus 1 squared is 1. And so when we take a root of a positive number and we say that it is 1.4, this is kind of a little bit of a convention. We can as well take negative numbers as roots, or both, and think of two roots, which we'll actually do soon enough. So if you are working with numbers a plus b square root of minus 1, which you denote by I, to be clear, so if you substitute sign of I and think that actually your correct way to take square root of minus 1 is instead of I minus I, you know, you should not get very different theory. I mean, after all, it's just a notation, and you know that I and minus I will be on absolutely equal footing, so they both are kind of nice choices for square roots of minus 1. If you choose kind of, I mean, there is no actual way to distinguish. There is no way to distinguish between two roots of minus 1. But, I mean, maybe in some ways there is, but it's really kind of philosophical. But if you fix one of them to call them I, then minus this thing will be another root, and you can use that to build your theory of complex numbers. And you should get the same object, right? And so probably this map, which takes my I to minus y, and then a plus bi to a minus bi, which is actually conjugation, should preserve all the properties, like send products to products and stuff like that, and indeed it does. So in general, there is an idea of a field automorphism, and this is that. So of course, it's very important to remember that conjugation of real numbers is real. What else? Maybe one more thing. So if you remember when we did this 1 over z, what we did, we multiplied by z bar and said that 1 over z is actually z bar over z bar, and the main idea was that z bar is real and actually positive. So z bar, if you just open brackets, will be nothing but a squared plus b squared. And this also is very important thing, it deserves a name. So absolute value of z is square root of a squared plus b squared. And this is funny because, I mean, you all know that square root of a real number is just square root of x squared. And now you know that this is kind of a special formula of more fundamental one. Anyways, so this is some things I wanted to say about complex numbers, and now let's come to geometry. So where an idea about geometry might come from, one thing is because we, after all, want to get sense of our formula cosine x plus I sine x power n equals to cosine nx plus I sine nx. By the way, notice that this mysterious formula already makes total sense for us because, I mean, this is a complex number, real plus I real, complex number, real plus I real, power n. You can take powers because it's a field that is very meaningful operation, and so this is something which is, I mean, checkable statement, you know, it makes some sense. But still we kind of don't understand why that happens, but we can use it or at least kind of think in this direction. So what is cosine x plus I sine x? So remarkably, remember our idea was pairs, and that a plus bi is sort of a pair a comma b inside R2. So as soon as you notice that for some reason there is like important to think about this cosine x plus I sine x complex number, you will definitely try to kind of draw this pair. And what is good about this pair is that it's actually drawable. So you know very well what it is. It is nothing but a picture where you have a unit circle, two coordinate axes. So this is 0, this is 1, this are, yeah. And then basically this is a point cosine x sine x. And we know that this point should correspond to complex number because, I mean, we know complex numbers are points. So then you just do it, I mean, let's just immediately generalize it to the whole sort of plane. So let's just identify C with R2, just identifying point AB with A plus BI as we already did. And this will basically now identify for us all points of the plane with complex numbers. In particular, this will be 1, and this will be I, because this is exactly 0, 1 thing. This will be minus I, this will be minus 1, and this thing will be like square root of 2 over 2 plus I square root of 2 over 2, and lots of other numbers, complex numbers. This is minus 1 minus I. And of course, this is not such a great idea, just because, I mean, we thought of them as pairs, and here we are. The next observation is a little bit interesting. So, addition of complex numbers, of course, is nothing but vector addition. And again, it's not surprising at all because this is how we defined it, so at the first place. But at least it gives us an idea that this geometric interpolation is actually, at least addition is very manifested here. But what you worry is multiplication, because multiplication is weird. And then you know that there is something relating this multiplication with this cosine x plus I sine x story. And so there is some hope to interpret multiplication of complex numbers from the perspective of usual plane geometry as well. And this is where you might get excited. So let's do that. That's actually very simple. So for this, let's just notice. So let's see. So definitely for points here on this circle, which are characterized by the fact that absolute value equals to 1, a squared plus b squared is equal to 1, right? It is meaningful to write, as we already know, to write the two parts of the number as cosine and sine. Let's do it for any number. So if you take arbitrary number, a, b, then of course there is one point which is kind of vector proportional to it, which has length 1. So if this is point AB, then the length, so let me call this 0z, so the length of the segment connecting 0 and z is of course nothing but square root of a squared plus b squared, and we even know the notation for it, it's just absolute value. And now we might want to actually write our number as something times absolute value, and this something is now presentable in this form, just because it is on the unit circle, and so for coordinates you can choose cosine x and sine x, and now x is usually denoted by phi, and this is just this angle, right? So this point will be cosine phi plus comma sine phi, and so it's convenient to think of z as equal to absolute value of z times cosine phi plus I sine phi. So this is triviality. So again, how that works? I take any complex number, which is any point. I look at 0, this axis is the axis of real numbers. I look at the angle, it's called phi. I look at the length, it's called absolute value. And then my claim is that my complex number equals to this absolute value times cosine phi plus I sine phi. And if you know what is this number, of course you can reconstruct. So A will be absolute value of z cosine phi, and B will be absolute value of z sine phi. So this expression is called trigonometric form. This is called trigonometric form of a complex number. And so probably you already understood that this form is very convenient from the perspective of multiplication them. And the reason is that we kind of already know when we multiply them, the phi's will add. And okay, so when we multiply such numbers as they stay on the right side without absolute value of z, then we checked that when we looked at Moivre formula before that the angles will add. And then we just might hope that maybe something nice happens with absolute values. And indeed, so a very fundamental and very simple statement is that when you multiply complex numbers, absolute values, which are just distances from 0, are multiplied, angles are added. So fundamental proposition, and let me say it in words. So, or maybe, okay, so let's say that z1 is equal to r1, which is maybe, so z1 equals to absolute value of z1 times cosine phi 1 plus I sine phi 1. z2 equals absolute value of z2 cosine phi 2 plus I sine phi 2. And then z1 times z2 is absolute value of z1 times absolute value of z2. And then we just multiply here and we get, according to computation we already did, cosine phi 1 plus phi 2 plus I sine phi 1 plus phi 2. And actually, this kind of is easy to see. Absolute value of z1 times absolute value of z2 is the same as absolute value of z1 times z2. So this thing is called argument of a complex number. This thing is called absolute value. And so when you multiply complex numbers, absolute values are multiplied, arguments are added. So as simple as that. So when you multiply two complex numbers, you add their arguments, you add their arguments, you multiply their absolute values. So you can start draw various pictures because it gives you some idea how that works. So if you have some number somewhere here and some number somewhere here, then this is Z1, this is Z2, I might, let's say Z2 is, Z1 is somewhere here. I might guess. So I see that sort of the absolute value of Z2 is roughly 2, absolute value of Z1 is roughly 1/2. If I multiply them, I will get something around 1. The argument of Z2 is this angle, which is, I don't know, like 65 degrees. The argument of Z1 is something like minus 30 degrees. When you add them up, you will get a number somewhere here. So this is Z1 times Z2. And you see, you can sort of using this idea, you can develop some geometric pictures, some machinery, how to actually multiply them. And moreover, you see that when you multiply a complex number, sort of other numbers are rotated and the whole plane is kind of shifted. So, like expand or something. And this is something which we will go to next time. So using this multiplication of complex numbers, you can reconstruct the whole series of isometries and actually isometries and similarities of the plane. So I will do it next time. That's a beautiful story. But before that, maybe let me end with two important ideas, or maybe one important idea. So okay, so one last thing I want to say in this lecture. So there is another way to write down this formula. So if you write cosine phi plus I sine phi as e power I phi, the thing we already did when we talked about power series, you will see that actually all these properties, that how you multiply them, for instance, will become trivial, because basically if this is Z1, this is Z2, phi 1, phi 2, then the fact that Z1, Z2 will be what it will be, it is just usual property of adding arguments of exponent. So from this perspective, you see that it is a very natural notation. At least it has the same property of exponents. The exponent of a sum is product of exponents, sort of extended to complex domain. And then if you take r being logarithm absolute value of z, then, which is positive number, so we can take it, then z, of course, just equals to, you can either say absolute value of z times e power I phi, which is the same thing as e power r plus I phi. And in this way, you can first think that you now can take exponents of complex numbers, which is kind of useful because any complex number is, of course, of this form. So now this makes total sense. But also you can think that actually you can sort of operate with them using properties of exponent. And this is called exponential form of complex number, and it's again extremely useful, especially in computations. And you can relate these two formulas by a very simple property. Just combining exponential form with trigonometric, you can derive the relation, and this is very simple. So let me just write it down. So if you know that e power I phi, is cosine phi plus I sine phi, you can change sign of phi, and of course you will get conjugate minus I sine phi. And then if you just solve the system of equations, you can find formula for cosine phi, which is e power I phi plus e power minus I phi over 2, and sine phi equal to e power I phi minus e power minus I phi over 2i. And this is, again, valid identities, and if you want to prove any trigonometric relation, in many cases it helps a lot because it reduces complicated trigonometry to just polynomial expressions, basically. Okay, so that's the end of the story. And in the next lecture, we will talk about isometries and similarities of R2 and explanation of this group of isometries from perspective of complex numbers.